Hi, in this video, we'll learn how cybercriminals can try to access databases by using a tactic known as SQL injection. SQL injection, otherwise known as SQLi, refers to an attack where a cybercriminal attempts to use an input field to write and run malicious SQL statements. Their goal is to gain access to and control an application's database server. If an application is not sufficiently protected, an attacker can use it to bypass an application's authentication and authorization processes. The attacker can retrieve the contents of an entire database, or they can add, modify, and delete records in a database. SQLi can provide an attacker with unauthorized access to very sensitive data, which could include customer data like passwords and credit card numbers, or personally identifiable information like social security numbers, cell phone numbers, and addresses. To run malicious SQL queries against a database server, an attacker must first find an input within the website or app that is part of a SQL query. An input is anywhere a user can place data, so it could be a place where you enter your name, email address, or a comment. Attackers can even use the URL of the site in the address bar. In essence, the cybercriminal is using an input on the client side of the site to access a database on the server side of the site. Let's take a closer look at the client and server relationship. A client can be compared to a patron in a cafe who orders from a menu. The menu is like the website. There may be portions of this database that are displayed to the client. In this case, the patron can see items from the drinks table and the dessert table. In each table, they can see fields. Here, the field T belongs to the drinks table, and the field cake belongs to the dessert table. The values listed for the T field are black tea and green tea. The values listed for the cake field are chocolate cake and crumb cake. The client makes a request to the server. I would like green tea, please. The server will now access the full database. Here, the server finds the drinks table and the dessert table. The drinks table is accessed and pulled up. In this table, we see the values listed for the T field. The value of green is retrieved from the drinks table and returned to the client. Here you go. All of this was done without the client seeing any aspect of the full database. Now, let's say the tables drinks and desserts are not the only tables listed in the database. Maybe there are other tables that should stay private and protected, like a table that lists the cafe's sales numbers, and a table that stores sensitive employee information. These two tables should not be available to the client and should be protected against SQLi. So how about a plot twist? What if this patron is secretly a disgruntled former employee and wants to gain access to the hidden database tables? She logs onto the website and clicks into the drinks menu option. She notices that the website lists the name of the table in the web address. What would happen if she changes the name of the table? When she types in dessert instead of drinks, the dessert table is displayed. Wonderful. I wonder if there's an employee table. So she types in employee. She's gotten to the correct place, but now needs a password. It's another input though, so she might still be able to access the database. Let's guess a random password. The most commonly used password is actually password. Well, that didn't work. But she wonders. Let's add a single quotation mark after the word password. This error message is actually good news for a cybercriminal. This means that the input field is not fully protected. To see what's going on behind the scenes, when the password is typed in, it is put into a SQL query. When the single quotation mark is added, it causes the SQL query to crash because now there's an extra quotation mark in the query. This is what led to the error message. So now she can use this to her advantage. She can now change the SQL query. She closes the password quotation marks and adds more commands to the query. She adds or 1 equals 1 because this is a true statement. 1 is always equal to 1. She also adds 2 dashes because this will cancel out the extra quotation at the end of the query by turning it into a comment. So what we have here is a query saying to show the table if the password is correct, or if 1 equals 1. Well, since 1 always equals 1, the table should be displayed, whether the password's right or not. We're in! Oh my, she was making a lot less than Jim. That's not fair. All right, so how do we prevent SQL injection? This is no good. One technique is to use server-side input validation. The server will check the input from the client and determine if it looks safe or not. That doesn't look quite right. You're going to need to input something else. Another technique is to use what is called an escape sequence for special characters. The escape sequence is different depending on the programming languages used to build the website. When escape sequences are used, the server will look at the input from the client and add a special escape sequence to each special character. This ensures that the special character remains part of the text and isn't used in the programming of the site or the database. I can input that, but I'll have to change it slightly. In general, it's good practice to ensure that there's no way to access the actual SQL query anywhere on the website. The SQL database should also be sitting behind multiple layers of protection, including the techniques we just discussed. All right, now it's your turn to go explore more about these concepts.